Kohlrausch proposed that any electrolyte at its infinite dilution, each ion contributes a specific amount of molar conductivity, irrespective of the other ion which it is associated. At infinite dilution, each electrolyte, the constituent ions, positive and negative ions, each ion will contribute a specific amount of molar conductivity. So, the total molar conductivity of an electrolyte is equal to sum of the molar conductivities of the constituent ions present in it. For example, if an electrolyte AB is completely ionized to give A plus and B minus at infinite dilution, positive ions will contribute some molar conductivity and negative ions will contribute some molar conductivity. If molar conductivity that exhibited by the cations at infinite dilution is lambda 0 plus, and for negative ions it is lambda 0 minus, then molar conductivity cap m is equal to V plus into lambda plus V minus into lambda minus. Here V plus and V minus are the number of constituent ions present according to the formula of the electrolyte, and lambda plus naught and lambda minus naught are the molar conductivities of cation and anion at infinite dilution. So, the molar conductivity of that electrolyte will be equal to the sum of this. For example, in NaCl sodium chloride, its formula contains 1 Na plus and 1 Cl minus. Therefore, number of V plus and V minus are 1 and 1. So, the molar conductivity of NaCl will be at infinite dilution Na plus Cl minus. For Na2SO4, 2 Na plus ions are there. So, 2 into lambda Na plus at infinite dilution plus lambda SO4 minus 2 at infinite dilution. If it is BaCl2, 1 cation and 2 anions are there. So, in such case it is 2 lambda naught at Ba plus 2 plus 2 into Cl minus naught. So, by that way you can get the molar conductivity. The molar conductivity is nothing but sum of the conductivities of total ions present at an infinite dilution. In case of weak electrolytes, we are unable to get this molar conductivity at infinite dilution. In an alternative way, we are going to calculate the molar conductivity by using the Kohlrausch law. For example, if you take CH3COOH, CH3COOH. So, its constituent ions are CH3COO minus and H plus ions. Now, the molar conductivity of CH3COOH is molar conductivity of acetate ions at infinite dilution plus molar conductivity of H plus ions at infinite dilution. But these values cannot be derived directly because CH3COOH is no more completely ionizable at infinite dilution. In the graphical method itself, we say that the limiting molar conductivity of weak electrolyte is not possible to determine, but in indirect way we can determine, which are having common ions, that is acetate ion and H plus ion. The salts are strong electrolytes which contain these common ions. With the help of those molar conductivities, we can calculate the molar conductivity of this. For example, we have a salt like CH3COOH. CH3COONA. It is a salt. Since it is a strong electrolyte, it is completely ionizable and it is a strong electrolyte. So we can determine the limiting molar conductivity of sodium acetate. By that way you can calculate CH3COO minus plus Na plus. So you are able to calculate the limiting molar conductivity of acetate ion and Na plus ion. You cannot conduct limiting molar conductivities of acetate ion and H plus ion from CH3COOH. But this acetate ions limiting molar conductivity can be calculated from sodium acetate. Similarly, the H plus ions limiting molar conductivity can be calculated from HCl. So limiting molar conductivity of HCl is limiting molar conductivity of H plus and limiting molar conductivity of Cl minus. So from HCl we can calculate the limiting molar conductivity of H plus. H plus ions limiting molar conductivity cannot be determined from acetic acid, but it can be determined from HCl. Acetate ions limiting molar conductivity cannot be determined from acetic acid, but it can be determined from sodium acetate because these two are strong electrolyte. Let us take another electrolyte which is NaCl. Limiting molar conductivity of NaCl can be determined because this is also strong electrolyte. It will be equal to Na plus plus Cl minus. Now, from this data, you can get this data. How it is possible? If you add these two and subtract this one, you will get, by subtracting means minus and this is minus. Now, if you add it, if you add these three, plus Na minus Na is cancelled, plus Cl minus lambda Cl is cancelled. Now, the remaining part is limiting molar conductivity of CH3COO minus plus limiting molar conductivity of H plus. This value will gives us the limiting molar conductivity of acetic acid. Experimentally, it is not possible to determine the limiting molar conductivity of acetic acid, but we can determine the limiting molar conductivities of strong electrolytes CH3COONA, HCl and NaCl. These values can be determined experimentally because they are strong electrolytes. From these values, you can derive indirectly the sum of the limiting molar conductivities of acetate ion and H plus ion. If you know the sum of the limiting molar conductivities of H plus and Cl minus, it will be equal to limiting molar conductivity of acetic acid. This is the application of Kohlrausch law, because the limiting molar conductivity of an electrolyte is nothing but the sum of the limiting molar conductivity of the constituent particles are present in that electrolyte. As weak electrolytes, limiting molar conductivities is not possible to determine experimentally. In an indirect way, by the results of strong electrolytes, we can calculate the sum of the constituent particles of weak electrolyte limiting molar conductivities, and it will equal to the limiting molar conductivity of acetic acid. So, if limiting molar conductivities of sodium acetate and HCl is added, from that sum if you subtract NaCl, you will get the sum of the limiting molar conductivities of acetate ion and H plus ion.